Uh, this is Lab 2, Charge Tapes Revisited. The purpose of this lab is to adjust our model of the charge tapes from Lab 1. The preview is that I adjusted my model from Labs 1. Instead of modeling each tape as a point charge, I modeled them as a line, evenly distributed charge. This is the model from Lab 1 using force, the electric field, and gravity, where we balanced the electric force and the gravitational force. And then this is the model from Lab 2. So we modeled each charge as a line of charge, and we modeled it as a bunch of little pieces of charge dq, and then we sum them all up with an integral. So each dq is lambda dl, where lambda is the charge density of the line, which is the total charge over the number of charges in this case. And then we have dE equals k times dq over r squared times r hat, where each r hat is those little green arrows. That's the direction of the electric field. And then this model also uses the concepts of electric force in Coulomb's law, the electric field, and the force of gravity to balance out the electric force. And the experiment, the system is the charge tapes, surroundings are this stuff. Those are the initial conditions. The experiment is just the same experiment from Lab 1, just recounting it here. The methods from the Lab 1 experiment, which this lab isn't really based on. Here's the coding. So in the code, I established a definition for the electric field from a given a charged particle and an observation location. And then the line charge function was given, and that just creates the objects as a line of charge. And then what I did was I used n equals 5 charges, and then I did some math to calculate the dE from the dQs. So for each dQ top in the top tape, we calculate for each dQ bottom in the bottom tape. So this is a nested for loop, so each little piece of charge on the bottom tape has an effect on each little piece of charge on the top tape. So we just go through all the top tapes and the bottom tapes like that. And then we calculate the little dQs, and then we multiply that we put that into the electric field function to calculate all the little dEs. We do the integral by just summing them up, which is the basic idea of the integral anyway. We use a discrete model instead of continuous model for this because we can just do it with a double for loop. And then we express that there at the bottom with the arrows, with the FE arrow and the FG arrow, and then we print the magnitudes. So for Lab 1 charge, I got 7 times 10 to the negative 9th coulombs. And then for Lab 2, I got 1.325 times 10 to the negative 8th, where we are assuming each tape had the same charge. If I had modeled each of my tapes as a single point charge, I would have gotten a significantly lower charge. In Lab 1, I needed 7 times 10 to the negative 9th coulombs to balance the tapes, but in Lab 2, I needed 1.325 times 10 to the negative 8th. And then these estimates differ because the fields where the charges are calculated behave differently, because the field from a point charge is very different than the field from a line of charges. So the second model is probably closer to the real value, since the tapes are better modeled as a line than a point. In conclusion, I adjusted the model of my charge tapes. Instead of modeling them as point charges, I modeled them as lines of equally distributed charge. I then recalculated my charge by plugging in numbers to make the electric field balance the gravitational field.